Welcome to Breaking Math, a podcast where we explore the fascinating world of mathematics and how it intersects with our everyday lives. I'm Gabriel Hesch, and joining me as always is my co-host, Autumn Thaneff.
Hi, everyone. Today we have a special guest with us, Matt Parker, a mathematician, comedian, and author. You might know him from his popular YouTube channel, Stand Up Maths, or his best-selling books, Things That Make and Do in the Fourth Dimension and Humble Pie.
Matt is here to talk about his latest book, Love Triangle, How Trigonometry Shapes the World, where he dives into the quirky and unexpected world of geometry, relationships, and the never-ending quest for perfection in shapes. It's a fascinating read that combines humor, math, and storytelling in a way only Matt can.
We'll be chatting with Matt about the inspiration behind Love Triangle, some of the mind-bending concepts he explores, and of course, how math can make you fall in love with triangles.
So grab your compass and protractor because you're in for a fun and enlightening episode of the Breaking Math Podcast.
I have one big question. Where did you get your page numbers from?
Yeah, so for people who are not familiar with the book, the page numbers start on page 0.000000. And not the first time I've started a book on page 0. My very first book, I've gradually done more and more ridiculous page numbers. In the very first book, I had to negotiate to start on page 0 instead of page 1, but they obliged. The page numbers then very gradually go up because they got like 6 decimal places of precision. They very carefully go up to 1, and they come all the way down to -1, and then they go back up to 0, pretty much 0 by the end of the book. And it's because each page you're looking at is the sine function of the page number as a number of degrees. And
I did the calculation, and I was going through each one, and I went,
excellent.
this is off by a smidgen.
Great. Yeah. Well, I had to stop at some point the number of decimal places. So how many pages in did you go before you started going, okay, what's up with these numbers?
Oh, I looked at it immediately for the
Great.
index.
Excellent.
And I went, okay, what mathy thing? I went sine, cosine, tangent. And I was like, all right, first I went for degrees, and then I went radians, and I went, what is he
Excellent.
doing?
That's
So,
the I
yes.
like to. So a lot, not to derail your question immediately, but a lot of people ask, because I'm famous for doing things online, doing YouTube videos and the like. And a lot of people are like, well, why do you write a book? And one of the things I like about the book is it's a physical object, and it's got page numbers, and it's got an index, and it's got all this fun book stuff. And so I always like to mess with those, given I have the opportunity. And so I want the experience of using the page numbers to give the reader an additional insight emotionally into something in the book. And
Absolutely.
so in this case, I was like, oh, this is great because you got that discovery of what do these numbers mean, and then you're doing your own little working it out, and then you're like radians or degrees, and then they're non-unique because, it's a sine function, so it goes through the same value more than once. And so I really liked the idea that as people are reading the book, they're getting all the same upsides and downsides to using a sine function, but in the page numbers. And Riverhead, the publishers of the book, were very, very supportive of my ridiculous ideas. And I wasn't allowed to make the book exactly 360 pages long. I did ask, but I was allowed to use the sine function of the page numbers.
Oh, my.
I absolutely loved it. I calculated what it was. 30. It went from 34 to 36, and I think that was the page that threw me off.
Uh-huh.
When I did it the first time, and I went, something is awry.
I'm going to have to because also in there, I've got some references about rounding.
Yes.
When you did log tables back in the day, the pros and cons of how they're rounded and ways that they were used to spot people breaking copyright, like copying someone else's log tables. And so I tried to put some of that into the page numbers as well. What I haven't done, I will admit, is gone through and verified that the exact page numbers I sent in are the ones that they put in the final book. And I considered writing some terrible Python code to take the PDF layout file they send me, extract the numbers and check, but I haven't done that. So if anyone finds a mistake in the page numbers, let me know. and I'll pass that up the chain of command.
Okay. Before we
Absolutely.
began this interview, I told you, Autumn, that I would only interrupt you if I had a really good reason to. And when you guys talk about Easter eggs, such as these ridiculous page numbers where they're trig functions, there's one that my former co-host, the late great Sophia Baca, has wanted to do. Sophia has loved making fun of page numbers where there's a page inserted that says this page intentionally left blank. What kid does not pick up a book and pick that up and say, why?
It's so good.
You're wasting it. So then Sophia got into this idea of self-reference and went crazy with it. Sophia would continue to put Twitter or X tweets or posts and Facebook posts where they'd put in parentheses, this post intentionally left blank. And then we did something ridiculous that is not good for our branding. We have an episode of the Breaking Math podcast you can find to this day called This Episode Intentionally Left Blank. Do you want to know what's in the episode?
That is it like 5 minutes of silence?
No, it's 60 minutes of silence.
That's so
No, I'm
good.
sorry. Static. It's static. It's
it's
just pure
static.
static. Yeah, but it
So
actually
you know
says
it's playing.
yes.
But
Yeah,
it's been left blank. That's so good.
Yes.
yeah, and like people are like, what is this? And then they read it this episode.
That's so good.
We and I'm sorry, our listeners. This was that may have bugged them, but you got to understand, we're making fun of the whole idea. So I love the idea of communication about mathematics, where you've got Easter eggs embedded into your own communication. Do you know of any other fancy ways of embedding mathematical ideas as Easter eggs into things?
Of
That's
course.
a great. Do you have a favorite, Autumn? I don't want to come because I all my favorites are ones I've done, and I need to think of one that someone else has done.
Oh God,
See,
no! If you want to tell us
I
your
do
own, go
a
ahead.
lot of mathematics integrated art or art
Oh,
integrated
amazing. Yep.
mathematics. So I would work up very complex origami problems with my students before,
Yep.
and I would break them down into very simplistic ways of folding or talking about applications for concepts. So think about a map.
Yep.
And this will even go back into paralleling into some of the stuff that you're doing with in the book. You have your map and you can just fold it into one sheet and you take it apart and have a big piece of paper. How do you do that mathematically? So those are like my little Easter eggs when I'm teaching a lot of complex art concepts outside.
There's a name for that folding pattern. I think it begins with M. I can't. Off the top of my
Muria
head.
map fold.
That's it. I was hosting a math fashion show a couple of weeks ago, and a friend of mine, Alianne McDonald, was like, "What are you wearing? What are you going to wear when you're hosting a math fashion show?" And I was like, "I don't know, like my normal outfit." And she's like, "No.
No.
So a friend of hers named Wenwin designed me a shirt based on that folding pattern and Fibonacci numbers. So the shirt folds out and then you put it on, and it's a Fibonacci in Mountain Valley pattern.
That is
in the
brilliant.
Shirt.
Yes.
It was incredible. But also, someone else at a conference recently gave me mathematical mittens, which I wasn't intending to show, but they're on there. Like I just was dumping stuff out of my case.
It was
'cause I'm on
meant
the
to be
road at the
today.
moment. Look at these. They're like procedurally generated mittens. So for people who aren't watching the video, they've got like lines zigging backwards and forwards at a seemingly random way, and they've been generated algorithmically. And I guarantee, this was a teacher named Emily, that probably the seed of this is like a phrase in binary or something like that. I'm almost certain there's like a hidden Easter egg in the starting of this, but I haven't decoded it.
Okay, math fashion show. That sounds incredible. Where did the math fashion show happen?
That's a good, yeah, you're right. It didn't just happen, on its own. There's a thing called the Bridges Math Art Conference, which is a conference for people who are either artistic mathematicians or mathematical artists, and it's kind of exactly what Autumn was saying. It's like the union, the intersection, the union of math and art, and people who talks about recreational math or interesting things I've come up with in terms of how it can be visualized, and artists talk about math that they've had to use in their artworks. And
Okay.
I have a huge amount of fun. going to the Bridges Math Art Conference.
Let's highlight
And
that
so,
because we've been talking about wanting to bring together mathematics and creativity for a very long time. So how is their social media presence? Is there a lot of stuff that you're aware of? Like, I don't know, on anything, Instagram or TikTok or anything of that sort?
that's a great point. I think the individual attendees, depending on their how old they are, will have different levels of online presence.
Okay.
But I don't know if the conference itself has that much online.
Okay.
But if you search for Bridges Art Math, you'll come across it.
Okay.
But I don't think they're putting much out there. They've been going for a while. I want to say early 2000s. They have a conference every year.
Awesome. Okay, yeah, I'm gonna look that up after this episode because that sounds incredible. I want to blow up our social media with that. I just do personally, but I have to talk to
It's
my
great.
co-host too.
I'm a huge fan of their work, and some of the attendees just do incredible stuff.
Okay, fabulous. Now I know, Autumn, that I had interrupted a few times there. Did you have more you wanted to ask before moving forward?
Go right ahead, Gabe.
Okay, awesome. Okay, so I in recent years I worked in computer modeling, and I learned so much that I didn't know before, and I love that because when you think you know everything, like about binary and compression and all that, and then you get into a new field like 3D modeling, you learn so much more. Specifically, I how do I say this? I was building 3D models for a certain client that needed vehicles and buildings done in anything like Maya or Blender, and then you texture them with anything, like Substance Painter, any of that stuff. And then just like learning how 3D rendering works and learning how 3D modeling is done with triangles and with quads. I knew this intuitively, but I realized as I'm reading it, I then learn it and consider it in a different part of my brain. There's like the practical side of my brain, and there's the reflective part. And I'm like, oh, you word it in a way that I knew intuitively. Anyways, I was wondering if, for our audience, if you could tell us a little bit about, I want to say it was chapters 4 and 5. I'm hoping to ask you if you can basically summarize the way you did how triangles are used in 3D modeling, as well as quads, and what's in the book in that chapter.
I'll give it as a I'm a lay nerd, and so for me, I get to dive into these areas for the first time. And so researching the book, I just kind of made a note. Oh, I know triangles are used a lot, like triangle meshes in video games and VFX and the like, because if you need to define a surface mathematically so you can compute it in a video game, it's a bunch of points and you link them up into triangles. I'm like, piece of cake. That chapter will write itself. And then I was speaking to a friend of mine, Eugenie von Tunzelmann, who does a lot of VFX for film. And she's like, no, we don't use triangles. We use quads. They're all quadrilaterals. They've all got 4 corners and 4. And I'm like, what? Why? Why would you use quads when you've got perfectly good triangles that are way easier to calculate right here? And she explained partly it's historical and partly it's still modern practicalities where triangles are just kind of hard to line up. And when you're making a model of something in 3D that's got like edges and like features, you want the edges of the shapes in your mesh to line up with the edges of the shape that you're modeling. And triangles just don't stack neatly. Whereas you can have a nice row of quads perfectly neatly all the way around the very edge of something. And in the book, I use the example of a UFO. You can line all the quads up around the edge of the UFO, get a nice crisp edge. But then once and also historically, it's been easier to generate surfaces using quads because early on, when you didn't have as much computing power, you can get a quad covered surface by multiplying 2 curves together and you get like their combined result as a surface. And that's always in quads. So I was like, oh no, she's like, Eugenie's just sunk my chapter. But then she's like, oh, but I guess we don't require them to be planar, so they don't have to be flat. And triangles, I mean, obviously I'm a big fan, you get flatness for free. Any 3 points, there's a nice flat triangle. Whereas a quadrilateral, you could have 2 opposite corners really high and the other one's very low, which means you're not going to have a flat quadrilateral. And Eugenie points out that they don't care if they're flat or not. So actually, every quad in a quad mesh is actually 2 triangles back to back. So my chapter was saved. They are triangle meshes, but they're triangle meshes such that all the triangles are in pairs that form quads that then form up the larger mesh. And so that was my journey of discovery as a tourist in the world of mathematical 3D modeling.
Nice, nice. And actually, what I read about, it was a problem that we exactly had. We were trying to model a certain vehicle that has, and again, I'm being vague on purpose because I don't know about my NDA and what I'm allowed to disclose here. We had a certain vehicle that had round parts and sharp edges. And when you talk about a planar thing, think about, a computer is trying to model something. The computer will simulate light and reflectivity. And when you talk about a planar surface, you've got, of course, as you said, 4 points that define a quad or a square. It knows exactly what to do about how to render the light when you've got a flat surface. But you take one of those points and you move it up and down so it's no longer in the same flat sphere. It has no idea what to do. And what it ends up doing is some weird approximation based on its parameters, where like if you tilt the model, suddenly it'll start flickering in that one spot, or the light will change all of a sudden. It has no idea. So that's why when you're modeling something with a computer, you've got to be very, very specific and think about, all of your vertices, all of your points, they've got to be in a flat surface here. But again, as you said earlier, sometimes you don't need them to be planar. Sometimes you do. For my purposes, I absolutely did. And one other fascinating thing, I've used this in job interviews. They say, teach us something in 30 minutes. And just off the top of your head, I always talk about computer modeling. Have you heard about how they simulate smooth surfaces when you've got polygon, jagged edges, how they simulate a smooth curve?
Oh, is that like a bezel curve or something like that?
I've used, so that I don't want to say no because I've used that term before, but like if you have, let's just say that you have a low polygon count of something where you've got like a hexagon that's supposed to approximate something that should be a cylinder. What you do is you do something. It's a very simple operation. I could just say you right click and you say shade smooth. But what it does is when the computer knows how the light is supposed to bounce off every edge. What it does is it takes an average of the directions, and it has a simulation where it smooths it artificially. It's still built with only polygons, but it just takes the directions and it has an algorithm where it smooths it, per reflection point. So it fudges it sort of. It's like blurring your eyes, sort of, if that makes sense. And
But what I love about that is, as you say, you can just right click and pick thing.
Yeah.
And a lot of students, when they're studying math at school, are like, I don't need to know the math, the computer does it for you. But if you don't understand the math, when you got your vehicle model, and as it tilts, a bit's flickering, if you don't understand, that's because there's some rounding in the approximation to simulate it as if it was flat. If you don't understand some of the math under the hood, it limits your ability to use the software. And I think that's such an important point. It's not just a case of the computer does it for you.
Yes.
And you're just free to be artistic. It's still beneficial to understand the math.
Yeah. What's also fun, this is a really, really quick one. There's something that's called either a normal map or a bump map or a height map, where if you imagine, in a 3D world where you make everything out of polygons, imagine if you've got like a cannon blast in a wall. It would cause so many polygons to map that. It's ridiculous. They have a way of approximating that as well, where you make one really high polygon count thing, and you can do it with a tool called ZBrush, where every single surface is modeled using polygons, and the amount of memory is ridiculous. However, you can take the information of the light bouncing off all those millions and millions of surfaces. You can bake it into something called a normal map, where just the information of the light bouncing off of it and not the information of how all those surfaces interact in 3D, but just how the light bounces alone. You can take that and then map it onto a flat surface, or even a surface with just like a couple of polygons. And the light behaves as it did with the high polygon surface, even though the actual behavior of the model is very, very low poly. That's how they do normal maps and bump maps, and you approximate something so that it looks gorgeous, even though it's very low poly. Does that make sense?
That's great. Yeah, you kind of you do the big calculation once to get the answer for how the light's behaving, and then you can just remember that answer. and not have to redo the calculation and then apply it to all your low poly versions. That's really nice. It's neat.
Yeah. So I don't know. I personally enjoy learning about how approximations and shortcuts are done for the purpose of 3D modeling when you need something to look pretty. And again, this is just for looking pretty, not for behaving accurately. Two entirely different. So physics-based modeling. Yeah. Physics and engineering modeling is different than visual or pretty modeling. And then the in this chapter, the other thing that I learned is the use of randomness in modeling and in computer generated thing. And I learned about Perlin noise and about how, you can map things to grids. I was hoping that you could summarize a little bit of that for our listeners. I think they'd enjoy it very much.
Yeah, Perlin noise is the random noise. And by noise, we don't mean sound in this case. It's not like a podcast left intentionally blank. It's like visual. It's like the static. For people from the past, if you remember a TV, it's like the visual noise. Someone named Perlin was working on the original Tron film, and they got upset at how terrible the noise was. And because if you're rendering things in a computer, it can look very computery. And for a long time, VFX looked very VFX because it's a bit too clean, a bit too perfect. Whereas in reality, everything's got a patina. It's got some damage. It's got texture. And not only that, but so that's one thing, you want to apply the random noise to your surface to make it look real. But also if you're, like you're saying, you don't want to model a million polygons at once to generate a whole forest. I can't plan every leaf out. You can use the random noise to randomly decide when you're growing leaves algorithmically. Like you can just, procedurally generate a forest. And Perlin wanted to come up with a nice mathematical way to do that. What they did ended up winning an Academy Award just for the noise, which I think is incredible. And there's two versions. There's Perlin noise and there's simplex noise. Both of them start with a grid. You assign random numbers to all the corners, all the crossing points in the grid. And then as you move a point around through the grid, you've got a way to calculate a new value for every in-between point based on the distance to all the nearby corners, and you use the distance to them and the value at the corner. You smush it all together in a big old function to give you an output. What's very nice about it is it's quick to calculate, and as you move around in the grid, the influence from all the different corners kind of ebbs and flows. Like as you get closer to a corner, its impact increases, and then as you go away from it, it decreases very smoothly. And so you get this nice smooth noise. If you did random numbers, it's very jarring and it's not very natural. Smooth noise is very natural. And the difference going from Perlin noise to simplex noise is the opposite of what we've just been discussing. Perlin noise was based on a square grid. Simplex noise is based on a triangle grid. And the reason that's helpful is you need noise in different numbers of dimensions. And that's partly because you might be modeling something in more dimensions. And it's partly because as soon as you start moving something, you want the noise to change with it or to control the movement, you've now got time. So you might want 4-dimensional noise or even 5-dimensional noise. So you've got multiple types of noise and paths you can move through it. And it's absolutely fascinating. And in higher dimensions, triangles that become tetrahedron, that become generalized tetrahedron, have far fewer corners and are quicker to calculate than cubes, because a square becomes a cube, becomes a 4D tesseract, a hypercube. And each time you go up a dimension with a cube, you double your number of corners, which stacks up very quickly. It's exponential. Whereas with triangles, you go up a dimension, you get one more corner every time. It's nice and neat and linear. And so because we suddenly needed higher dimensional random noise for video games and VFX and all these things, we switched to triangles because they behave better in higher dimensions. And I love that a knowledge of higher dimensional shapes and meshes and lattices informs practical visual effects. Well, not practical effects, but practical application of digital effects. I find that so fascinating that we need to understand higher dimensional objects to make movies.
Yeah, no, that's awesome. Or even movies, but also generally speaking, just storage. Like if you need to store enough, if you need to compress data and store it, because, storage fills up fast. Just knowing that, as you said earlier, a 4-dimensional, you take a triangle and you make it in 3D. It is the tetrahedron.
Tetrahedron?
Yeah.
Yep.
Like that part just astonishing to me. How much less data, a 4-dimensional and 5-dimensional triangle based shape takes than a cube or even something else, and then how you use that to store information. That's huge. That's huge. And then this chapter got me thinking about even like forensics. Now I realize this is a little bit of peripheral from just talking about triangles, but the approximations of noise. I was astonished at how a grid is not noise. A grid is very ordered and repetitive, but you can still play with it and assign it different things where you have an approximation of noise. It made me think, okay, so if you wanted to like really use some forensics and figure out if something is like truly random as in nature, or if it's random, it made me think, what would be the difference between a very convincingly or a very convincing Perlin noise that's not truly random and an actual random thing? I don't know. I'm curious though now,
That's interesting. I imagine there would be a way of doing it. I've met forensic accountants before, and part of their job is teasing apart accounts to see if they have the right amount of randomness that you would get from organic expenses, costs, etc., versus cooked books like artificial accounts, where someone's making up random costs. That randomness is very different to natural randomness. And I imagine if there was someone doing like a video analysis of like, is this very convincing AI or is this a real video?
Yeah.
Potentially, and this is obviously us just speculating.
Yes.
Potentially, what you could do is try and analyze the noise in the video on the surfaces. Was this like mathematically generated, nice, neat, simplex noise, or is this like actual natural noise? And I haven't come across anyone doing that, but I would say there's a decent chance that's possible and will be used before long.
I got a mind blower here for you. This is something that is pretty well known at this point, but what really from a psychological perspective, the perception of randomness is also very different than true randomness. I'm sure you know about the original iPod and the complaints about the iPod Shuffle. Do you know that story?
Yeah, the original one was properly random, and people were complaining. They were hearing the same song again too soon. It's because it's properly random. It's not the iPod. It's not shuffle. I mean, shuffle would be different, I guess. It wasn't the iPod random.
So what's funny is less random actually has the appearance of more random, and there's reasons for that, and it gets into the psychology of expectation and things like that. So I don't know, all of this just fascinates me. And then the last thing I'll say, and I thank you for the time, Autumn. After this, I'm going to toss it to you for a while. Speaking of using forensics to determine frauds from the real thing, my wife showed me a show on Netflix. It was either a year ago or 2 years ago, I forget. It was about the fraud of the in Mormon history in the United States. There was a book. It was involving a salamander, a white salamander, and it turns out that there was a trader of Mormon artifacts this last century who was extremely smart, complete fraud, but his IQ was off the charts, and he would create these fake books, but then he would artificially age them using like a fish tank and electrolysis and humidity, where he would give it the appearance. And, for all intents and purposes, actual people who know how to age things are like, oh yeah, the exposure to the air, this only, this kind of entropy only happens after it's aged. It took new science, brand new understanding of aging to prove that he was a fraud. Did you ever watch that show?
No, but that's phenomenal. I guess the financial motivations for a good fraud are pushing forward the barriers. New science to do good fraud needs new science to unpick it.
But then
I did it's not quite that. It wasn't a deliberate fraud. I came across a painting, a copy of the Mona Lisa, when I was writing my book. And for a long time everyone knew it's just a copy. It's just a copy of the Mona Lisa. Obviously it's not worth as much by a long shot because it's just someone copied it. And then when they were cleaning it, they realized, hang on a second, it's not exactly the same. Everything was subtly different. And they realized by using the mathematics of parallax, where you can analyze the viewpoint and how things in the foreground, as you move your viewpoint around, they change and shift different to things in the background. They were able to analyze the parallax in this copy of the Mona Lisa and realize it was painted by someone else at the same time as Da Vinci to the side and a couple, I think a meter or two closer, they could pinpoint the exact location in the room this other painter must have been looking at the same model, painting at the same time.
Oh my
I think it's
God.
incredible. By using math and, geometry, we could determine this isn't a copy. It was one of Da Vinci's students in the same room painting concurrently with them, which is just phenomenal.
Wow. And the motivation for that too. Like you can like with the dude with the Mormon book, I imagine so many folks would just give up and be like, "Yep, it's real. The scientist guy said so. Yep, it's real." But then somebody else had to try themselves to say, "Is it even possible to make this up?" And I think they analyzed the statistical distribution of the entropy, and they saw that when you do something quickly, the entropy happens in a different pattern than when you do something slowly over many years. But that wasn't known. He had to literally try to assume it could be done, try to do it, then under a microscope, and like that motivation, like
That's
he was
amazing.
driven. You know what I mean? Like who would just give up and be like, "Oh, it's real." Like I don't know, man. So
And
yeah,
that's great because everyone else, if you make the fraud or you own the fraud or you want to sell the fraud or buy it,
yeah,
everyone's motivated to just come on. That's not. It's real. It's real. Who's asking more questions? The scientist said it's real. But to have that curiosity, that no, how could it be done, and can I work it out myself, and can I detect it? That's
yeah.
I find that fascinating just thinking about we have the calculation, sometimes we put it out and we think that there's all these additional variables. You have to think of things in like a closed or a black box, right? One example that I know that you were talking about a little more in the book was about playing pool,
yes.
right? So I know that you've gone in depth about that, but when you're playing pool and looking at triangles and the trigonometry behind that versus the application in real life, how does that exactly work
Yeah.
out? I've seen the behind the scenes on a couple of your videos with that and was fascinated by it because I love playing pool myself.
Excellent. I'm a lay pool player. I love playing it, and I always find it very pleasing that it seems to be largely angles, trajectories, geometry. I'm like, I love it. I can do this. And so we decided to put that to the test. So I joined forces with another mathematical friend of mine, a guy called Grant Sanderson, who does the 3 Blue 1 Brown YouTube channel, if people are familiar with that. Grant's great, also adequate at pool, like me. We made a good team. And then we challenged a pool YouTuber, someone called Rolly Williams, who also does a fantastic climate change channel. Just, it was worth mentioning. Climate Town, which is amazing. And a professional pool player, Jennifer Beretta. We played them. We didn't play a game. They set up one of their challenges because when they're training to be better at pool, they do these little practice shots over and over and over again, little training exercises. And they set up one for us where the goal was you got to kind of bounce the cue ball off 2 of the cushions or the rails, and then you got to hit another ball on the far side of the table. And so Grant and I got out our measuring tape. We measured the distance from the cue ball to all the rails or the cushions, and then we work out exactly where it's got to end up. And then we put our cues down and we went and drew some diagrams, and we approximated it as if it was like a particle of light bouncing off a mirror, like a perfect angle in equals angle out situation, which, spoiler, is not. And then we worked out exactly what we had to do. And I think the fantastic point you're making, Autumn, is this generalizes where it's all well and good to simplify a system to a point where it's easy to calculate,
Yes.
which is what we had done. But then you got to remember, hang on, I've probably thrown out a lot of nuance, which might be fine, or I might have thrown out something important. And any mathematical model, you've got to pay very close attention to what you're assuming, what you're ignoring, all those sorts of things. And we had ignored a couple things. The friction on the table, for a start, but that's kind of fine. The friction of the cushions, now that's a problem, because as a ball hits a cushion, it gains spin, and we'd ignored the spin. And so we had a point particle bouncing perfectly as an actual ball with momentum and rotation, and it hits the thing, it starts to spin. And once the ball's spinning, so the first collision we were pretty good, because it came in with no spin, bounced off the cushion, great. But now it's gained spin. The next cushion it hits, that spin changes the angle it comes off at. And so it opens up the angle. So because it's spinning kind of into the cushion, it makes it come off on a more shallow angle. And so our shot was way off because we didn't factor in the spin. And what was very interesting was talking to Jennifer Beretta, the pro player, about what professionals do when they're playing pool. She was going, well, they'll often look at a distant point in the room that they aim for. And they were using the same techniques we were using. They were imagining the bounces off the cushions as if, instead of light reflecting, there's a whole mirror table that it's going into, and a mirror reflection and another mirror reflection. And they're using those same mathematical techniques, but without realizing that's what they're doing, which is great. Like, I don't know if someone came up with them originally mathematically or just they've evolved people playing pool, but they're very math-based techniques under the hood, but they've got a layer on top of that where they understand the physics of how the table behaves and how even the humidity in the room changes the friction on the felt. It's phenomenal. And Jennifer showed us some calibration shots she does. This isn't in the book or the video or anything else, by the way. This is behind the scenes. She's got a bunch of calibration shots. So when she's going to play in a new pool hall or a new competition, they get a bit of time on the table first, and she will do these set shots and look at how the ball responds, and she can then use that to calibrate exactly how much friction, spin, and everything there is on this specific table and cushions. And then she can then play the game using her normal techniques, but she knows how to compensate for this specific physical reality of the table, which I found absolutely fascinating.
I actually find that to be fascinating as well. And just seeing how we take all of these problems within physics and then we translate that from the math, and just seeing how that correlates to what you have in the book and how the book covers some of the interesting mathematical curiosities, right? So we have everything from the discovery of new shapes and polygons. And I'm a bit curious on what you found to be one of the most intriguing mathematical problems that you explored when going through writing the book.
Yeah, that's a good question. And I would say I got distracted looking at how shapes are discovered, but it's like a passion of mine is like a lot of people kind of think that math was done by the Greeks and then we haven't really touched it. We just learn it now. And like maths in the past. And I really want to emphasize that it's an ongoing subject. We're still discovering new shapes to this day, and we're still learning new math and coming up with new techniques. And I accidentally came across, I forget why, I was researching like something about shapes with like 8 corners or something. And I came across a paper written in 1962 by someone called Donald Grace, who was trying to find the biggest shape. And by the biggest shape, I mean, if you had a shape with, let's say, 8 vertices, so you got 8 corners, and you confine it within a sphere, just because you can imagine scaling it to be as big as you want. But we want to say, what's the most efficient shape if you can arrange 8 corners on a sphere to form a polyhedron inside? So what's the biggest 8-corner shape, basically? And it's not a cube. Cube has 8 corners, and you think, well, that's pretty good. And actually, a cube is the way that you can distribute the corners so that they're the greatest distance from each other. Like a cube's the most even distribution of the corners. But that doesn't work. That doesn't give you the biggest volume. And what Donald Grace did was fire up a computer and use some techniques at the time that were completely novel, but now they're very standard computer search techniques to try and get a computer to search for the arrangement of 8 corners such that you get the greatest volume possible. And they discovered a new shape. They discovered a shape that's got a bigger volume than any other shape with 8 corners. And it was later proven that that's the optimal. And there were 2 things I liked about that. And one is that some of these problems are still unsolved. There's always new shapes we don't know about. And even that question of arranging the corners so that they're the greatest distance from each other, we don't have a way to solve that in general. Like you couldn't give a mathematician, you're like, I want, 53 dots on a sphere as spaced as possible. They're like, I don't know, good luck. I can probably get a computer to try it. But that's an unsolved problem. We can do it if they match a platonic solid like a cube or an octahedron or something.
Yes.
But not in general. And despite all the funding from Big Golf Ball, we've not found a way to arrange dots on a sphere, which I find phenomenal. But also what I found incredible is I think this shape that Donald Grace found in 1962 using a computer, using the Burroughs 220 for retro computer fans, is the first shape ever discovered by computer. And now, modern, like practical applied math, industrial math, it's like using a computer is the same as breathing. Like everything's done on a computer. Computer searches are like the bread and butter for industrial math research. Whereas Donald was just curious about if a certain shape existed. And as far as I'm aware, and I'd be very keen to hear if there's any prior examples, this was the first time someone ever then programmed a computer to search and find a solution to produce a shape, which I think was such a seminal moment in shape hunting in the human millennia-long mission to find and document new shapes.
Absolutely, especially when you're looking at the advances of technology and how from then to now, if you're looking at the mapping of that and just seeing how that evolution goes for computer graphics and programming. And normally we take that triangulation into everything that we're doing for movement, right? So when you're trying to program something just as natural as hair all the way to simulations of soft tissue robotic surgery with finite element analysis, you have to consider all of that programming and simulation modeling every single time.
Yeah, and it's like we were saying before, there's a lot of interplay between that and art. And as you were mentioning, obviously, you mentioned the finite element analysis.
Yes.
That's, in engineering, that's just such an incredibly valuable tool, but it's not dissimilar to the meshes and things that are used in VFX. And so something we're using for
Correct.
visual rendering is not wildly different to practical.
So when you're doing a lot of that for the VFX all the way to the finite element analysis, that's actually the same simulation software behind the scenes a lot of the time.
It's
And
phenomenal.
a lot of the people who do those graphics are the same people who are doing the video game graphics.
Yeah, and a lot of people are like, a lot of math people are like, well, what's the point of that? Why are you doing that? And
Right.
It's very similar to art in that regard. It's because it's beautiful, it's wonderful, you want to do it. And actually, at the Math Art conference I was at recently, there's a group called Nervous System. They do some phenomenal generative jigsaw puzzles and other phenomenal stuff. And this is going to be my terrible paraphrasing of what they do. But check out their work if you're at all curious about this. But they were using ways to procedurally generate. So like you give the computer, like, generate something that kind of matches these requirements, and the computer would do it. And they're using something called Voronoi diagrams, which is where you start with random points, and then each point gets the region around it, which is all the points closer to it than any other point. And you get these very organic looking structures. And they were doing that to like generate like a skirt, like the mesh for a skirt, by generating that using very organic looking results from very computer algorithms. They were then involved in using very similar techniques that they developed for things like making skirts and fashion and sculpture. They were then employed to help model human organs by using the same techniques to, like, how would you build a lung from the ground up? And it's a very similar kind of fractal organic pattern. And so the same techniques they developed for artistic reasons, they were then applying very practical ways to generate and make artificial simulations and models of human organs. And so I think it's very hard to draw a line to say this math is useful, this math is pointless and just used for art or for curiosity's sake, because it all bleeds from one to the other.
Yeah, I just thought of something when you were talking about I'm sorry, I can't say it right.
I think it's Voronoi, but
Voronoi,
my pronunciation is famously flexible.
I have seen that term on my Blender software. It's one of the procedural
Yeah, there
things
you
you
go.
can drop in. And as you were talking about that, briefly in my head, this is probably not even accurate, but I thought that sounds like the simplex algorithm you described earlier for noise, but kind of in reverse, sort of, not really. But then I thought, when you take simplex noise, you start off with the grid. How doable, I wonder, would it be to do that process in reverse during forensics? That is, take a data set that you think appears random, and could you do like the simplex algorithm in reverse and just see if you could wind up at a grid and use that method to compare simplex noise to organic natural noise, or noise that, or like a noisy surface that you would see in nature? Then that brought up the further question of whether there really truly is actual randomness, or whether everything is dependent upon some other ordered, I don't know, ordered source. Long set of questions there. So
I'm gonna park that second question for a second, but I think the first, I absolutely. I mean, and then again, this is me speculating off the top of my head. If you took a random, like a surface with like random noise on it, you could like pick all the local maximums for whatever the noise, like the darkness of the pixels or something, and a Voronoi. There's probably better techniques, but it's not a bad way to imagine how you'd reverse that. So a Voronoi would be to take all the maximum points, and then you draw a region around each one, which is all the pixels closest to that maximum compared to any other maximum. And you might start to recreate an original mesh or grid that was used to generate the noise. Of course, with the simplex noise or Perlin noise, there's scaling because of the values. But that's also what nervous system were doing. They would then apply, so instead of having a real homogeneous, what do you call it, the same in every direction situation, they could scale it in different directions or add different densities or distort it to get not just a pure random Voronoi looking series of cells mesh, but one that's got certain properties in different directions or bunches up in different regions. So I imagine there might be similar techniques to reverse that. But you're right. I think, if you look at random noise, potentially doing something like that might, if it reveals underlying structure, that might indicate it was artificially generated. But then again, I don't know enough about true naturally generated noise as opposed to just pure randomness, what that would display. It'd be like the book again. You'd have to analyze both cases, spot if there's any intrinsic differences, and then reverse engineer the math as to why that might be happening.
Okay.
So out of all of the topics within the book, what did you find to be the most surprising thing?
Oh my goodness, the most surprising thing across the book.
Yes.
That's interesting. What surprise? I mean, the meshes not being triangles surprised me. That was startling.
Or
you know
something
what?
that you significantly left out and wanted to talk about.
Oh my god. Well, that's a very long list. I mean, the most
Right.
surprising thing was that when I came up with the idea for the book, I actually pitched this book idea, a book about trigonometry, about 10 years ago, when I was a very new author. It was like my first ever book proposal. And I was like, oh, I think there's not any kind of real popular math, like real, not like a textbook, like a real general book for anyone about trigonometry. And I put together a proposal, and my publishers, so I published with Penguin Random House, they were like, nah, we're not convinced. And then 10 years later, I'm like, you know what? I still think there's a book about trigonometry out there. And I didn't know if the gap in the market was like an actual gap that needed filling, or just it was a terrible idea, and that's why no one had done it. But I was like, I'm going to do it. And I was surprised that I was spoilt for choice. I was kind of wondering, because I had like a rough idea what the book was going to look like. I mean, until you start writing it, and you're like, I haven't got enough chapters, or what am I going to put in? I thought this chapter would be easy, and I can't find enough examples. I had an embarrassment of riches. I was like, oh my gosh, there are so many amazing stories about geometry and trigonometry and things being used out there. The thing that kind of got cut was when I realized I had so much other geometry and trigonometry stuff to talk about. I had a whole section at the end about Fourier analysis, which is decomposing signals and data into individual sine waves. And because I was talking about sine functions and the page numbers are technically a sine wave, which I find very pleasing. It's like the world's worst flick book. That I want to talk more about now what we can do now we understand sine waves. And that was the bit that then got a bit compressed, partly because it was the bit that was least perfect for putting in a book, because some things lend themselves to being bookified and some don't. And talking about sound and music and sound waves and images and stuff, that was less likely. And so I was surprised that there was just so many things I could put in the book. And the one bit I'm kind of sad didn't make it into the book is I was writing a whole thing and looking into using waves and Fourier analysis to compress images. So like JPEG compression is,
Yes.
and I thought it was so amazing that an image is compressed using what we consider sound waves, but they're just waves. They don't care about sound. And so that, I think, I'd written a whole thing about it, but it was one thing too many for the book. It got cut like in the early draft, and I was very sad about that. But probably the most surprising thing, to change tack slightly, is that ocean waves are not sine waves. And so I've got the list of things that are waves. There's like sound, that's a wave, like electron, like quantum physics, they're all sine waves. I was like, light, sine wave, everything's a sine wave. And then suddenly ocean waves are like, nope, not sine waves. They are a different type of wave. And I was like, well, that's good. And I mentioned this in the book. I'm like, I'm glad there's at least one wave that's not a sine wave. It's fundamentally a different wave.
Definitely. The next book is going to be all about waves, right?
Oh, that'd
It
be
should
awesome.
be. It really should be. Yeah.
As an electrical engineer, I completely promote that. And also, along the lines of what you're talking about with compression and with Fourier analysis, I want to go ahead and plug another creator. I don't know if you're aware of Art of the Problem. He focuses on mathematics in electrical engineering and computer engineering with a lot of machine learning. One of his older videos is in collaboration with IEEE, and he talked about a type of compression where the decoder is wrapped up in the code packet along with the message itself, and it just like unfolds and decodes itself. It's it's an amazing video.
I highly recommend the channel. Yeah.
Oh, you've seen it before?
Yes.
Oh, fabulous. He's a great guy. Yeah, he was our first interview for this season, actually. We talked about the mathematics behind Chat GPT-4, as well as the book. There's a book on a brief history of intelligence. Great chat. So yeah. And until Mark comes out here and kicks me out, I'm just going to keep asking questions. Do you have any recommendations for science and math content creators and teachers who want to go on YouTube and make it?
Oh, to create or to absorb?
To be successful.
Create.
Like if you're a creator, like
yeah.
What's the magic
That's a
to
tough
make it on
one.
YouTube? Okay.
Yeah. I mean, I absolutely love YouTube. I love creating videos. But I was a high school math teacher for several years.
Okay.
And so, but also at university, I was into making short films. And I'm old enough, I remember when YouTube started, and I was like, oh my goodness, this is perfect. Like, the downside to making video before that was there was just no way to share it. I mean, there was rudimentary stuff online. And I was like, this is great. And I can combine my passions of making videos with talking about math. Just practically, the problem with YouTube is at the beginning, it's a lost leader. Like, you got to do it as a hobby to start with, because I started doing YouTube in earnest, and it took 4 years before it was paying for itself in terms of my time and effort being put into it.
Yes.
And I'm very fortunate. I had the privilege to spend 4 years doing that because my wife is a salaried physics professor. So I can do that, right? And not a lot of people can just, down tools doing other work and do something. So I would say my one bit of advice is you got to enjoy doing it. And it's sad to say it's got to start as a hobby, because it's not going to pay its way for a long time.
Oh.
And that's unfortunate. Also, at the beginning, you're a one human band, because you've got to light and edit and sound and everything else. And so my advice, because I loved editing, but I'm not good at sound. But sound is key. Like visuals, you can get away with terrible visuals on YouTube as long as people can hear you clearly.
Yes.
So I had to lean on some friends. Yeah, Autumn knows exactly what this is like. People will tolerate awful visuals, but keep watching. But if the sound is hard to follow, they're gone.
Right.
So I got advice from some friends, and I just found it kind of standard. Plug and play. I do the same thing every time, and it's good enough
Okay.
technique. But then I think philosophically, in general, the reason why we do it is I feel like there's so many wonderful things in math. These wonderful moments when you discover something or you learn something new, and just the beauty of the patterns and the logic behind mathematics is incredible. But it takes a lot of background learning to reach some of those points. And not everyone has the time, energy, inclination to do all that work to achieve that at the end. So I always think of being a math communicator or making content online about mathematics is providing a shortcut. So I'm like, what is it about this bit of math that inspires me or I find so pleasing? And what's the shortest path from where most people are to a rough approximation of that sensation? And so that's my goal is always, how can I give people an insight into all the things that I love about math without them having to spend years getting a degree or studying it recreationally or whatever the case may be. And so that's always my kind of guiding principle. And in general, as a litmus test, I am my own audience. Not exactly, but to a sufficient approximation. And so I always think, what would I like to know? What did I enjoy the most about investigating this topic? And then I make the video I would have wanted to have watched before I started on researching it myself. And so and it's not guaranteed to work. I just got very fortunate. It's a survivor bias. There's 1,000 of me who started out making YouTube videos, and I just got lucky that the type of stuff I enjoy making and consuming myself, other people do as well. So
Nice.
I also
Nice.
take all my advice with a grain of survivor
Nice.
bias salt.
I have one last thing I was hoping I could share. Autumn, I hope it's cool with you. I wanted to share our idea of how we're gonna make it big on TikTok with TikTok Shorts or whatever. I've wanted to do this animation where I'm sure that we all know the cultural impact of things like Dragon Ball Z, that are just these ridiculous cartoons, or any other like fighting cartoon or game like Street Fighter 2. What I've wanted to do is have a series of problems, math problems, that look very, very difficult at first glance, but are actually almost trivially easy as long as you know what to do. And I wanted to have something show up like in Pokemon, how it's like a wild whatever has appeared, or in Dragon Ball Z, some threatening monster appears that looks all scary, and then the hero knows what to do. Like, oh, if all you do, first of all, is multiply it by e, or multiply by this coefficient, or do this one little thing, or L'Hopital's rule, for example, it suddenly becomes much less threatening. I want to have some kind of yeah. You know what I mean? Like
it's like Street Fighter, where a problem appears, but if you know the special move, it's like up, up, down, down, left, right, L'Hopital's rule.
Yeah.
Yes.
And good, love it. I'm on board.
He throws that fireball and he says like Hadouken or whatever.
Yeah.
But like instead, L'Hopital's rule. L'Hopital's rule.
Factorize. Yeah, love it.
Yeah.
Yes.
Just do something. And that comes from my own teaching experience. I was a big storyteller, and I would have an assignment for my kids. I'll say, write me the hardest math problem that you can think of. And if they're like in 4th grade, they'll be like, what's 1,000,000 plus 1,000 plus, you know what I mean? And like think it's some impossible thing. And then you learn that's just a trivial repeated thing, and then you learn a new concept. We did that, and we got as far as exponents. What is the scariest exponent that you can write? And then we would, we'd come up with one, and then we'd show them the magic trick to solve it. I just want to do that with animation, and I want to see some student go super cyan, you know what I mean? And then solve it using this trivial thing, and be like, oh, it's that easy. So when I have all the time to animate, I'll have time for that. I just don't have time for it. So
I know that feeling.
Yeah. So I think that's it. But it has been an absolute pleasure, and the book was very, very enjoyable. And I'd like to give you the last words, Autumn, since I took more than my share.
I'd just like to actually thank you for coming on the show today. And
my pleasure.
I have one big ending question, small but big.
Okay.
What is the number one thing that you want people to know about the book, about mathematics, and just take away from it?
Yeah. No, I think that small thing was my original motivation to do a book about trigonometry, which is, I think it's a shame that a lot of people think math is just what they were forced to do at school. And the reason I picked trigonometry and things like Pythagoras is I think that's the most advanced math that most people were forced to learn at some point. And so it's become this kind of mascot for math is hard and pointless and awful. And isn't it great we can avoid it now? We're not at school.
Yes.
I think that's a real shame. So my one tiny big thing from the book is to reevaluate, for people to reevaluate what they thought math and specifically geometry and trigonometry was from school, because it's not, I mean, being a teenager is the worst time to be forced to learn anything. I just want people to give math a second chance. It's not what you remember from school.
Wonderful. Thank you so much.